Hey everyone, it's Mr. Kabbalah. This is a lesson on unit number 9, section number 1 on the introduction to statistical testing. So let me know if you have any questions and enjoy.
All right, so this is an introduction to statistical testing or hypothesis testing. So here we go. The first step is to establish a working hypothesis about a population parameter. This hypothesis is called the null hypothesis. N-U-L-L. Denoted by H and then a little subscript 0. So I'm going to say it as H naught. You might hear some people H null, H 0, or H O, but I have been saying H naught for a while. The null hypothesis is a statement that is under our statistical investigation or statistical testing. It represents a statement of no effect, no difference, or things haven't changed. Any hypothesis that differs from the null hypothesis is called an alternate hypothesis, denoted by H1, and sometimes I've seen HA, but I've always used H1. This is the statement we will adopt in which if we find that there's evidence against H naught or the null hypothesis and we reject it. Typically, the alternate hypothesis states that the actual measurement is greater than, less than, or not equal to the measurement given in the null hypothesis. A statistical test is designed to assess the strength of evidence so the strength of evidence and data against the null hypothesis. So as examples, example 1, an auto repair shop says that it takes an average of 25 minutes to change the oil in passenger cars. So the null hypothesis would be that the mean, or mu, is 25 minutes. A possible alternate, so a possible H1, is that mu is, let's say you say it takes longer than that, so greater than 25 minutes. Example 2, television networks claim the average length of commercial breaks during a 60-minute show is 12 minutes. So the null hypothesis would be that the average, mu, is 12 minutes. You might say that a possible alternate is that it's actually less than 12 minutes, which I don't think could happen with commercial breaks. And then example 3 kind of already done for us. The average height of professional basketball players is 10, or of basketball players 10 years ago was 6.5 feet. So that's the null hypothesis, that mu equals 6.5 feet. Professional basketball players are taller today than they were 10 years ago. That would be our alternate hypothesis. So that would say that mu is greater than 6.5 feet. So here's one. A car manufacturer advertises that its new subcompact models get 47 miles per gallon, or MPGs. Mu is the mean of the mileage distribution for these cars. You assume that the manufacturer will not underrate the car, but you suspect that the mileage might be overrated. So you might suspect that 47 miles per gallon is a little higher than what it actually is. So what would H naught be? What's the null hypothesis? That our mu is equal to 47 miles per gallon. What's our alternate? Is that mu is probably too high, so it's more likely less than 47 miles per gallon. So with the exercise, maybe try it on your own and then move forward, pause and then move forward to see if you get the same thing. But in this one, it's talking about ball bearings being manufactured for other places that need them. So it says that the average diameter of a certain type of ball bearing should be 6.0 millimeters. So that's going to be our null hypothesis, that the average, mu, is 6.0 millimeters. What's our alternate? Well, it just says to check that the average diameter is correct, the company formulates a statistical test. So if our null hypothesis is saying that it's 6 millimeters, then our null hypothesis is saying that it's not 6.0 millimeters. So it could be more, it could be less, just not 6.0 millimeters. So based on your alternate hypothesis, you might have to pick a different type of test. So first of all, the null hypothesis, H naught, always states that the parameter of interest equals a specified value. The alternate hypothesis, H1, states that the parameter is less than, greater than, or not equal to that same value. So there are three types of tests. There's left-tailed, right-tailed, two-tailed, and it kind of goes along with less than, greater than, not equal to. So less than, greater than, not equal to. And that's kind of what it says in all of that. I'm not going to read that to you, but basically what the tail they're talking about is on a normal curve. Okay, so you've got left tail, right tail, and two-tailed, so here and here. So that's what they mean by tails. On here, basically it just summarizes what was just said. It tells what type of test to use, so left-tailed, right-tailed, or two-tailed, depending on if it's less than, greater than, or not equal to. It says, while we are going to concentrate on tests involving the population mean mu, other parameters can be statistically tested as well, like population proportion, the student's t distribution, the difference between population means, and so on. All right, so there's something that I don't have a slide for, but we'll write it down here. Basically, what this does is it transforms a test statistic into a z-score. I'll give you the formula, but your calculator actually does this automatically. But the test statistic, and let's for argument's sake say that we're doing a sample mean x bar. What we can do to change that to a z-score is to take our sample mean, subtract the mu, and then divide that by the standard deviation divided by the square root of the sample size. This piece in the denominator is actually the standard deviation of the sample mean distribution. But that's how we go about getting a z-score. Now your calculator does that for you anyway, but there's the formula in case you ever want to do it by hand. So p-value of a statistical test. The p-value of a test statistic is the area under the normal curve that is more extreme, either lower than or higher than, so it says in either direction than the sample mean x bar or whatever test statistic you're looking at. I think throughout this section we're going to be using x bar. The p-value is sometimes called the probability of chance. The p-value can be thought of as the probability that the results of a statistical experiment are due only to chance. So as kind of what's going on here, if you're dealing with a standard normal curve, then what you'd have here is 0, and you'd have these z-scores. So let's say we have a z-score of, so a z-score, so I'm going to put a little x bar there. So that's kind of our sample z-score. In fact, let's label that. So z-score of sample or test statistic. And then we're looking at the more extreme part. So in this case, to the left of that. And this area, that would be our p-value. Now don't confuse p-value with the lowercase p we use for the proportion distribution. We typically use a capital P dash value, p-value. In case we are dealing with just not the standard normal, you'd have your mu here. You'd have, let's say, your x bar value here, and then this area that I'm shading in would still be your p-value. So the reason I did this is basically you can either use z-scores or the test statistic, because your calculator actually does a pretty good job of this. So just to get an idea of what a left tail, right tail, and two tail test would look like in terms of a normal curve, left tail test, you have your mu right here in the middle, and the left tail test would go in this direction. So this area would be your p-value. A right tail test is when we're trying to find greater than the sample, in this case, the sample mean. Again, here's your mu. This would be your x bar. So this would be the p-value right here. And then a two-tailed test basically is saying that it's not this mean. So it could be below or above in either direction. So, technically each of these areas is the p-value divided by 2, but you put them together and you get your p-value. So here's a little graphic of what a p-value tells us. A low p-value tells us that the results, it's unlikely that the results were obtained by pure chance. It's likely results could be repeated in similar tests. So that's a low p-value. A high p-value is that it's likely that the results were obtained by pure chance, unlikely that they could be repeated. So what I thought of is if you deal yourself a hand of poker, so poker hand. Okay, if you know anything about poker, you know that maybe a royal flush is, unless you're dealing with wild cards, it's the best hand you could get. I believe so. Or is it four of a kind? I'd have to look that up, but not the point. A royal flush is 10, jack, queen, king, ace, all of the same suit. So if you deal yourself a royal flush with a thoroughly shuffled deck, that is going to have a high p-value because you obtain that most likely by pure chance. Okay, so high p-value there. That's just something I came up with as an example of high p-value. As an example down here, a statistician is conducting a statistical test and obtained a sample mean of x bar equals 80 while testing against a null hypothesis that mu was actually 65. The statistician calculated a p-value of 0.04. What does this mean? So what the p-value tells us, it means that x bar, so the sample mean, which was 80, was probably not caused by chance. And that the results could be repeated by another statistician, which also means that the sample mean stated might be wrong. Here's an example, and it's going to use the calculator eventually. Rosie's an older Pekingese dog who gets regular checkups from her owner, who happens to be a veterinarian. Let X be a random variable that represents Rosie's resting heart rate in beats per minute. From past experience, the vet knows that X has a normal distribution with sigma or standard deviation of 12. The vet consulted various informational websites and found that for dogs of this breed, the population average is 115 beats per minute. Over the past 6 weeks, the vet has tracked Rosie's resting heart rate in beats per minute. And there they are. The vet is concerned that Rosie's heart rate is slowing. Does the data indicate that this is the case? So let's first get a null and alternate hypothesis. So the null hypothesis, so H naught, would be that the population mean given is true. Okay, our alternate hypothesis is that the mean, now she's trying to test to see if her dog's heart rate is slowing. So we want to check to see if it's less than 115 beats per minute. Okay, so less than 115. Now, if your calculator does a good job with this, if I switch to my calculator here, where you would go is stat and over to tests, and they're going to call it, it's actually number 1, it's called a z-test. All right, now if you take a look at what we need, now you can use data, but we're going to do stats. This mu with a little 0, that's mu naught. So that's the population mean that we're testing against. So in this case, it's 115. This would be our standard deviation, 12. Now we need to figure out the x-bar. That would be the sample mean, and then this is the sample size, which turns out to be 6 pieces of data, sorry. And then down here, we have to tell whether we want to do not equal to, less than, or greater than the given population parameter. So we're going to test less than. So to get this sample mean, one way to do it is you could do it by hand. You could add them all together and divide by, in this case, 6. Another way to do it is if you hit stat again, and then edit a list, go to L1, and I actually did this for all of the examples in this section, but in this L1 here, I have the 93, 109, 110, 89, 112, 117. So you type those in, you can go to stat again, and then again, we want sample mean. So if you go over to calc and do one variable statistics, and you might have to change the list. So I know its default is L1. I've been playing around with it. I have it at L5. To change it back, I'm going to hit second stat, and that brings up my lists. It brings up a list of lists, and I want to use list 1. All right, so it's going to give me now all of the data, all of the calculations for L1. And you can see at the very top, the sample mean is 105. So again, go to stat, over to test, z-test, and it somehow actually changed it for us, right? And what we're going to do, now you could actually take a look at the drawing, where we're going to calculate. And what it tells us, this first line just kind of tells us what we typed in. This converts it to a z-score, so it's negative 2.04 as a z-score. That would be 105 as a z-score. It gives us our p-value, 0.021. Again, the lower the p-value, the more likely it's not caused by random chance. So what we can do, let's go back to our notes. Okay, it says determine the p-value and interpret what it means in the context of this situation. So the p-value was equal to 0.021. And what that means is that since it's low, it means that the results were unlikely to be caused by chance. It also means that these results could be replicated. Excuse me. It also means that the original population parameter given, so mu equals 115, might be wrong. Now notice I use the word might. And what that is, so what we would do is we would reject the null hypothesis, so basically saying, we don't think that's right, and then adopt the alternate hypothesis. So we're basically saying there's a 2% probability, so where I got that 2% right here, 2% probability that the sample mean we calculated was oh crap. Oh no, I was right. Now let me start that again. So 2%, I got that 2% from right here. There's a 2% chance that the sample mean was caused by chance. And 2% is pretty low, so that means it's probably not caused by chance. If you want to look at a little picture here, I'll kind of do both a standard normal and using the data. So, here's 0. Now on the calculator, it gave us a z-score of negative 2.04. So it's way down here. And then also if we use, here was the 115, so 105 is actually way down here. So yeah, it's most likely not caused by chance, that there's something going on here. So that's why we reject the null hypothesis and adopt the alternate hypothesis. So moving on from there, we're going to talk about errors. Now this can get a little confusing, but we'll do the best we can. Types of errors. All right, so like we just did, we rejected the null hypothesis. So if we reject, basically meaning that we don't think it's right, if we reject the null hypothesis and it turns out to be true, we have made what is called a type 1 error. And I use a Roman numeral 1. Now, if we accept the null hypothesis and it turns out to be false or wrong, we have made what's called a type 2 error. Now, usually we do not know if an error has been made. Therefore, what we do is we talk about the probability of making an error. So it is good practice to announce in advance of testing the amount of evidence against the null hypothesis that will be required in order to reject the null hypothesis. So basically we say, we will reject this if, and then we give kind of a, what probability we're going to use. This probability, this is called the level of significance of a test. It is the probability with which we are willing to risk a type 1 error. And a type 1 error is where we reject the null hypothesis and it ends up being correct. The level of significance is usually represented with a Greek letter alpha. It looks like A, it's a little more scripty, but it's alpha. In other words, the level of significance, so alpha, so I kind of make mine look like a fish, is the probability of rejecting the null hypothesis when it is true. It is a probability of a type 1 error. Now, for a type 2 error, there is a probability for that. And we use the Greek letter beta. So it looks like an uppercase B with a little tail on it, and it's beta. In fact, those are the first 2 letters of the Greek alphabet, alpha, beta. Alphabet, get that. We typically try to make alpha and beta as small as possible, and alpha is usually picked first. So we actually pick the alpha. We'll get to that. Now the quantity 1 minus beta, so basically the opposite of the probability of making a type 2 error. So 1 minus beta would be the probability of not making a type 2 error. We call this the power of the test, and represents the probability of rejecting the null hypothesis when it is actually false, which is actually what we want. So that's something we want to happen, whereas a type, we don't want the error anyway. A note on terminology. This is kind of confusing to me, that's why I put this in here. So when we accept the null hypothesis, or when we say this might be true, we also can say that we fail to reject the null hypothesis. We don't reject. So I'm going to put that maybe down here. We don't reject. Now, why don't they just say we don't reject the null hypothesis, or we're accepting it? Don't know, but you're going to hear fail to reject quite often. Sorry about that. Now, this does not mean that we have proven the null hypothesis to be true. So again, we're not proving it. It just means that the evidence in favor of rejection, so the evidence of saying this isn't true, that evidence isn't strong enough. Now it's out to talk about being in favor of rejection. I've had plenty of that. Did I just say that out loud? All right, and then here I kind of gave a couple of pointers. Fail to reject the null hypothesis, reject the null hypothesis. You can read through that. You can kind of see on a normal curve where we would reject the null hypothesis and where we would fail to reject or accept the null hypothesis. Again, the next little section, types of errors. So the truth of the null hypothesis, if it's true and we fail to reject it. So if it's true and we fail to, I'm sorry, it's the correct decision. We haven't made an error. But if the null hypothesis happens to be true and we do reject it, that's the type 1 error. Now, if the null hypothesis is false or wrong and we fail to reject, which means we accept. So again, that phrase is confusing to me. And again, why don't we just say accept? Because I think with accept there's connotations of it's true, but fail to reject simply means we don't reject it. I guess that's where we're coming from. Anyway, if the null hypothesis is false or not true and we accept it or fail to reject it, that's a type 2 error. Where if it's false and we then reject it, that's what we're supposed to do. So down here you can kind of see where the probabilities come in. Right here is our alpha, or our level of significance. Okay, so alpha is the probability of causing a type 1 error. Right here is the probability of not causing a type 2 error, and that's called the power. We are going to mainly look at the level of significance, but it does say the power of a statistical test increases as the level of significance increases. So for example, a test performed at alpha equals 0.05 level has more power than one performed at 0.01. This means that the less strict we make our significance level alpha, the more likely we will reject the null hypothesis when it is false. Okay, and down here I gave a little graphic of what a level of significance means from 0.01 to 0.10. We typically use a level of significance of 0.01, sometimes 0.05. I don't know if I've ever seen it 0.10. I just put that on there as the end. But you can kind of see what happens as you move to the left and move to the right. So it says using a larger value of alpha, or the level of significance, will increase the power of the test, but it will also increase the likelihood of a type 1 error. So despite this, statisticians in all types of industries tend to choose very small alpha values, usually 1% to 5%, 0.01, 0.05, because they are more willing to make an error by failing to reject a claim than to accept another claim that is actually false. And we will be concentrating on the probability of a type 1 error, alpha. Let's go back to that statement. They're more willing to fail to reject a claim. So statisticians are more, they would rather accept a claim than to accept a claim and then have it be false. So they're more willing to chance a type 1 error than a type 2 error. So here's an example. Consider the problem about ball bearings. They make ball bearings 6 millimeters. We were considering the manufacturing specifications for the diameter. Again, our null hypothesis was that the average was 6.0 millimeters. Our alternate hypothesis was that they're not 6 millimeters. So in this statement, or in this situation, we are testing this statement. The ball bearings have a diameter of 6 millimeters. That's our null hypothesis. If that turns out to be true, which means that the ball bearings actually have a 6 millimeter radius, if we decide, yeah, that sounds right, then that's exactly what we should do. Okay, we made the right decision. If they're actually 6 millimeters and we say, nope, no way, it's got to be something else, that's a type 1 error. Now, if the population means, and somehow we'd find this out later on, but if we find out that they're actually 6.8 millimeters, so if the null hypothesis is actually false, and we say, yeah, 6 millimeters sounds right, that's a type 2 error. Whereas if it's false and we say, nope, it's got to be something else, then that's the actual right decision. Now, moving along with in context of this, suppose the manufacturer of the ball bearings requires a 1% level of significance. What would a type 1 error do in this situation? So again, that's where we would, if we made a type 1 error in this situation, then the ball bearings actually have a diameter of 6 millimeters, but we are the ones saying, nope, it's got to be something else. It's a type 1 error. What would happen in that situation? Probably in this manufacturing scenario, we would make adjustments to machinery or computers or whatever they use that don't need to be made. And then that, if you're, shutting down production to, recalibrate machines when they don't necessarily have to be recalibrated, then you're slowing down your production and shipping and all that other stuff. Now, what if you make a type 2 error in this situation? So that's where the diameter is actually different, but we're saying, yeah, the 6 millimeters is right. That's fine. Well, we don't make adjustments or calibrations. So we don't make these adjustments when they should be made. And send out or ship defective ball bearings. And if somebody's going to get a shipment of defective ball bearings, they're not going to be too happy. So neither case is great, but a type 1 I think is a little less significant than a type 2. Type 2, you send them out, they're unusable, whereas type 1, you're kind of slowing down production. All right, so concluding the test. So we have two big values that come about. We have the p-value and the alpha, or level of significance. So those are the two things we compare in a statistical test. We compare the p-value against the level of significance, which again is the letter alpha. I make mine look like a fish. So here are the two cases. If the p-value is less than or equal to the level of significance alpha, we reject the null hypothesis and say the data are statistically significant. So you kind of say, the data that I'm looking at are significant enough to say that this hypothesis is not true. Now, the word significant in this case means at the alpha level of risk, the evidence or sample data against the null hypothesis is sufficient to discredit the null hypothesis. We then adopt the alternate hypothesis H1. Now, two things. We do not claim to have proven or disproven the null hypothesis. Basically, we have discredited it. So it's not that it's true or false. It's just the sample that we got discredits that null hypothesis. And number two, we can say that the probability that a type 1 error occurred is alpha. So in this case, I think they said a 1, so a type 1 error occurred, the probability that that happened is 1%. Now, again, going back to p-value versus alpha, if the p-value is greater than alpha, we do not reject or fail to reject the null hypothesis, or we accept the null hypothesis. Now, again, that does not mean that we're saying that it's true. We're just saying that the data that we collected and the test statistic we used isn't strong enough to say that it's not, we can't discredit it. So here are the 5 basic components of a statistical test. We went through all 5 real quick. You got the null hypothesis, alternate hypothesis, and level of significance alpha. Then we do a test statistic and sampling distribution. We've been using X bar, or the sample mean, calculate p-value, and then you test that p-value against your level of significance, alpha, and then interpret the results. So here are a couple of examples we're going to run through, and your calculator does a lot of this for you. Now, I'm not going to read the whole thing to you, but basically there's a creek. They're testing ammonia nitrogen concentration because a golf course and a housing development moved in, and the EPA is afraid that the fertilizer that the golf course and housing developments the fertilizer that those things are using is harming the concentration levels of the creek. So in any case, they take data. It says construct a statistical test to examine the claim that the concentration of ammonia nitrogen has changed from 2.3 milligrams per liter. We're going to use a level of significance of 1% or 0.01. So what is the null hypothesis? So if you actually did read all of this, it's saying that the average concentration is 2.3 milligrams per liter of water. Now, our alternate, okay, basically it says to examine the claim that the concentration has changed. So either greater than or less than. So what we're going to say, not equal to 2.3. So based on that, are we going to be doing a left-tailed, right-tailed, or two-tailed test? Left-tailed is less than, right-tailed is greater than. We have not equal to, so it's two-tailed. What is the test statistic and corresponding z-value and p-value? Draw a sketch. So this is where you go to your calculator. So let me pop that up here. And again, like I said, I type mine into the list. So I want stat edit. I have those concentrations in L2. You don't have to do it that way, but that's what I did. So I went to stat, calc. Now I have to change the list. So second stat again to give me a list of lists. Change it to L2. Calculate, and this gives me my X bar, 2.5. So then let's get our p-value and our z-score. So I am going to hit stat, test, choice 1, z-test. And we're going to fill in all of this stuff. So the mu naught is 2.3. The standard deviation, if you go back, it says so in the problem is 0.30, so 0.3. Our sample mean that kind of fills it in for us, 2.5125. We have 8 that changed for us, and we are doing not equal to. Change the color of the drawing, but we're just going to calculate. All right, so the z-score is 2.00. So if we were doing a standard normal, this would be 0. Now, because we're doing two-tailed, that would be -2 and +2, and the area to the left and to the right of those. All right, so our z is 2 and -2. Now the p-value, if you go back to your calculator, it gave us a p-value of 0.001. 0.045. Now, letter D, compare the level of significance and the p-value. What is your conclusion? So 0.045 is greater than our level of significance, which is 0.01. Okay, if the p-value is greater than alpha, we do not reject H naught. Okay, or another way to say that is we accept H naught. Now again, we're not saying it's true, but this is if we go to the interpretation. What we're saying is there is not enough evidence to suggest that the mean ammonia and nitrogen concentration has changed from 2.3 milligrams per liter. So we don't know if it's exactly true, but the tests we did, not strong enough. So here's another example. This one doesn't necessarily go through the calculator work. It kind of just goes through writing hypotheses. The Weather Channel uses a writing system to classify nor'easter storms that frequently hit New England states and can cause much damage near the ocean coast. A severe storm has an average peak wave height of 16.4 feet. Suppose that a nor'easter is in progress at the severe storm class rating. What would be the null hypothesis? So in this case, the null hypothesis, H naught, is that the average wave height is 16.4 feet. So if we wanted to test if the storm is getting worse, what would our alternate hypothesis be? Well, if the storm is getting worse, then those waves are getting bigger. So is mu greater than 16.4? What if we wanted to test if it was dying down? Well, then our alternate hypothesis would be that the average wave height is decreasing, less than 16.4. What if we wanted to test if we didn't really care if it was dying out or getting worse, we just want to know if it's changing. Well, then that's where we would use that the average is not 16.4. Couple more. All right, let X be a random variable representing dividend yield of bank stocks. We may assume X has a normal distribution with standard deviation 2.4%. A random sample of 10 bank stocks gave the following yields. All those. Says for the entire stock market, the mean dividend yield is 4.7%. Do these data indicate that the dividend yield of all bank stocks is higher than 4.7%? So our null hypothesis is that it is 4.7%. Our alternate, what we're going to test, is it greater than 4.7%? Right now, calculator can do it. Again, I have mine in, stat, edit. I believe I have mine in L3. Okay, so I'm going to hit stat. I'm going to calculate the sample mean. I got to change it to L3. So my sample mean is 5.38. So again, stat over to tests. All right, so our population mean is 4.7. Our standard deviation is 2.4. Our X-bar was 5.38. There were 10 of those, and we are testing, is it greater than what they're saying? So we're going to go down to calculate. All right, now I'm going to mainly just look at the p-value right now. It's 0.19. So 0.19. Let's test that against our alpha, which is 0.01. 0.19 is greater than 0.01. Okay, so what that means is we fail to reject, okay, which means we don't reject the null hypothesis. Okay, so we kind of keep this. Okay, now it doesn't prove that it's 4.7%. It could be true, but our data is not strong enough to support changing it from 4.7%. Okay, a zoologist studies hummingbirds, Grand Canyon. They're talking about weight in grams. Gives us the standard deviation. It gives us the mean. And we want to see, do the data indicate that the mean weight of these birds in this part of the Grand Canyon is less than 4.55 grams? So our null hypothesis is going to be that the average weight is 4.55 grams. Our alternate is going to be that it is less than that. Okay, so again, we need to calculate the sample mean. So stat, I have it in, I believe it was L4 this time. Calc. So I get an X bar of 3.75. All right, so we are comparing it to 4.55. The standard deviation was 0.70, so 0.76, and we are checking to see is it less than 4.55. All right, so I'm going to look at the p-value at 0.003. 0.003. Now our alpha was 0.01. So 0.003 is less than or equal to 0.01. So what that means is we reject H0. So we're saying this is probably not true. And then we adopt that they're probably less than 4.55 grams. Now, again, we're not saying that's absolutely true. We're just saying that our evidence suggests that the null hypothesis is, we have discredited it. Discredited it. I think I'm saying that right. That sounds weird. And we have discredited it enough to reject it. All right, last one. Last exercise and then a little graphic. Nationally, about 11% of the total U.S. wheat crop is destroyed, blah, blah, blah. It gives, those numbers are percentages of wheat crops destroyed. It is known that the standard deviation is 5%. So here we go. Stat. I have it in L5. Right now, if you noticed, I did not equal to, I forgot to formulate my null hypothesis and alternate. So the null was that the average is 11%. So our alternate would be, it just says is different, either more or less than the national average, so not equal to 11%. All right, so I got a p-value of 0.23, and 0.23 is greater than 0.01. That's our alpha. Like I said, alpha will typically be 1% or 5%. So what this means is that we fail to reject H naught. Now I'm going to add on here at the 1% level. That's the level of alpha. Okay, which means we continue to keep thinking that that is true for now. Our data suggests that our data is not strong enough to say it's probably not true. So it's not discredited. So we fail to reject. Now, why do we compare the p-value and alpha? So right here in the middle I have alpha. So imagine this is the 1% or the 0.01, right? If the p-value, so if the p-value is lower, so imagine the p-value down here, then what ends up happening is that we reject the null hypothesis. And then we adopt the alternate hypothesis. You can kind of see on the left why that might be true. If the p-value is actually over here, this is where we fail to reject. Okay, and you can kind of read through that. A lot of this is confusing, but your calculator does most of the work. What I would say is the biggest thing is learn how to use your calculator, and then you're really just comparing the p-value against the alpha or level of significance to see if you should either reject or fail to reject the null hypothesis. So let me know if you have any questions. I know this was a longer video. Sorry about that. If you have any questions, let me know, and hopefully you're doing all right. Bye now.
So here's just a quick alternate way to do the z-test. If you already typed in your data into a list, so like I showed you on this video that I typed all these into a list. So you could hit stat, over to test, z-test, and if you actually do it using data, then it turns to this where it asks you which list do you want to use. Now you still have to know the population mean of the null hypothesis. You still have to know the standard deviation, but those were given to us in the problem in this section. And then you just have to hit second stat to get to your list of lists, and you can go from there. You still have to know which test to use, not equal to, less than, or greater than, but then you don't have to go and get the sample mean and then go back to the z-test option. So an alternate way to do that.